Hey guys! For activity 4 practice, we are going over how to calculate correlations in Excel, and then we'll also go through some examples on how to run various analyses in SPSS. For the most part, the procedures for this week are fairly simple. We will be doing some graphing of scatter plots. We've done this before in Excel a couple activities ago, but I also wanted to show you how to use the chart builder in SPSS so that you can build graphs in SPSS if you want to do that instead of Excel. Our general instructions for the activity are pretty much in line with what you've seen before. So after you're done with the practice videos, you can go in and take the quiz that's associated with this activity. For practice 1, all of our calculations will be focused in Excel. So I've given you a set of data that have some fitness test results from high school students, and all of that will be in the sheet labeled Practice 1 in your practice data set. So I've outlined a couple of tasks that we'll be doing in the spreadsheet. We'll make a correlation matrix that shows all of the correlation coefficients for the bivariate relationships between our variables. We'll also calculate the coefficient of determination and kind of go over how we might interpret that value based on a specific example. And then lastly, we will create a scatter plot. I'm only going to do one example between push-up and pull-up data, but in your quiz, you might be asked to look at the relationship between other variables, where I can't ask you to paste a graph into the quiz, but I can ask you things like if we've identified some variable as the independent variable, what axis would that be plotted on? Or based on your scatter plot, what does the relationship look like? Or what's the r-squared value and what does it mean? That type of thing. So nothing super crazy, but there will be questions somewhat related to what the scatter plot shows and how you might interpret what the data are looking like in there. Down here I've got some helpful tips just in case you might need them. And with that being said, I'm going to change my screen over to our Excel spreadsheet. The first thing we're going to do in Excel is create a correlation matrix. So make sure you're on the practice 1 data. And then I'm just going to copy and paste my data labels in both the horizontal as well as the vertical directions. So now I've kind of got a matrix looking outline, if you will. If you recall from our lecture, in a correlation matrix, we have this diagonal line down the center that will represent all of the perfect correlations between like variables. So at this intersection, mass correlated with mass should give us a perfect correlation because all of the mass values are being compared to each other. So there should be a one-to-one relationship. We could test this out by using our correlation function, which is just equals correl. And then when we define the criteria for this, all we have to do is insert a range of data. So in this instance, because I'm plotting mass against mass, I would choose that cell range twice. And then you can see we do in fact have a correlation of 1. So this is kind of acting as the divider between the top half of your matrix and the bottom half of your matrix. Which half you decide to fill out is completely up to you. I personally like to fill out the bottom portion, but if you want to fill out the top, or if you want to fill out both just to see how things turn out, you're more than welcome to do that. For now, I'm going to make the top half gray because any correlation coefficients that we calculate in this area will be the exact same values that we get in this bottom area. So to begin, we can use our correl function, and this particular cell is going to give us the correlation coefficient for the relationship between the number of push-ups a person can perform and their mass in kilograms. So it really doesn't matter which range of data you list first, because mass is our kind of like our first variable in the column. I'll choose that one to go as my array number 1, and then push-ups would go as my array number 2. And then what I can do is format my values so that they show to 2 decimal places. That's more or less what we'll commonly report our R values to. So you could easily set your entire table to 2 decimal places if you wanted to, and then just make life easy and automatically fill like you want it. So we could go in and individually put the function for every single relationship between mass and some other variable. We can also make this function copyable as we drag in a downward direction. So recall, if we copy downwards, the row references will change. And given that our data are kind of set in a certain number of rows, we don't necessarily want that to happen. So up in our function bar, what we can do is add a $ in front of our row references. And then if we copy this function downwards, all we have to do then is change the variable that shows up in red, or the second array that we've identified. I think I did that one wrong. Yeah, second array that we've identified in our function. Now I'm paranoid. I'm going to double check. Okay, so this one would go to 500 swim time, and now we've got these lovely things calculated. To fill in the rest of the correlation matrix, all we have to do is click and drag. Now push-ups would be our blue variable, and then the variable we'd be modifying by dragging the box around would be the one that's in red. So I would look at push-ups and pull-ups, because that's the variable that is in this cell. There we go. I could change this one to shuttle run, to 1.5 mile time, swim time, and 500 meter swim time. Okay? And then you just keep repeating that for the rest of your data. Now, if, I know functions are new, correl I feel like is a pretty easy function to remember in relation to correlations, because that's what it sounds like. But if it's helpful for you to just practice inserting the function multiple times, I would not hate on you for doing that. Also, can't really see what you guys do when you do your activities, so who am I to judge something I know nothing about? Anyways, I laugh at my own jokes. Here we go. Nice. So, now we have a correlation matrix filled out, and we can see in here that all of our values are between 0 and 1, or 0 and -1, which is what we want. That's the range of values that we can get for any R. specifically a Pearson's R. So when we have negative values in our table, such as negative 0.17, that would indicate a negative relationship. Okay, so if we plotted this on a scatter plot and put a trend line in the middle, it's kind of a weak correlation, so the line might be more horizontal than we want it to be. But generally speaking, the trend line would go in a downward direction if you're looking at the line from left to right. That would indicate that as one of our variables increases, the other one is decreasing by some unit value. Okay, so the sign, whether it's positive or negative, is going to tell us the direction of the relationship. The actual value is going to tell us the magnitude of the relationship. So I already mentioned, like, this would be a weak relationship. If we were looking at like 0.45, that would be considered more of a moderate relationship. If we were looking at 0.7, that's a strong relationship. Okay, when you're actually interpreting the strength of your correlation coefficients, it might be helpful to go back to the lecture notes to look at what the criteria are for weak, moderate, and strong. But pretty much that's correlations and how we calculate them in Excel. Now, if we wanted to calculate the coefficient of determination, I'm just going to do this for all of the variables because why not? And because I'm OCD with formatting, I'm going to put them over here. Okay. And then what I'm going to do here is just delete all of the values in my table because I'll be strictly going off of the values that are coming from the correlation matrix that I made. So I'm going to leave this yellow line blank. Pretty much what should happen is if we calculated the coefficient of determination by squaring 1, we would just get 1. If we multiplied it by 100, we would get 100%, right? So that would indicate that any variation we see in mass is explained by itself, which completely makes sense because the same values are being compared to each other throughout the relationship or throughout the scatter plot if we plotted them. For values that do not have a correlation coefficient of 1, the easiest way we can calculate our coefficient of determination is by doing equals. And then you'll recall that when we denote the correlation or the coefficient of determination, it is r squared. Okay, so if we said r, which is our correlation coefficient, put a caret next to it, and then a 2, that would square the r value that we have referenced. So I could press enter, and I can either get my coefficient of determination as a decimal. Alternatively, I could also multiply it by 100 if I wanted it listed as a percentage. Okay. From here, this is a repeatable function, so I could then calculate the correlation, or I keep wanting to say correlation coefficient. I could calculate the coefficient of determination for any of these other r values. Okay, and then this is totally copyable, which is great for us because that makes life super easy. Okay, and then I would again recommend that you double click in any cell just to make sure that the reference value is what you actually want it to be. But in this matrix now we have all of our coefficients of determination, and when we talk about let's do draw. When we talk about coefficient of determination, we used a Venn diagram. So let's say that we're looking at the relationships between push-ups and mass. So this would be the r squared value that I'm referring to specifically. Okay. Let's say that our red circle represents the number of push-ups someone can perform, and then I'll make a blue circle for the mass. Okay. Now, let's say that there is some degree of overlap between these two variables. That area right there represents the r squared value, which in our case came out to be 49.60%. So what this would mean is that, well, I guess it depends on like which way you're looking at it, but it would mean that 49.6% of the variability we see in push-ups, let's say, is explained by its relationship with mass. Hopefully that makes sense. If we were looking for the coefficient of non-determination, that's 1 minus r squared, and basically that would be anything that has not overlapped between our two variables in our Venn diagram. So anything that's not green, basically. Okay, and that area would be represented by 1 minus r squared. So if we did 100 minus 49.6, I'm doing it on my calculator, we would get 50.4%. So this, or coefficient of non-determination, would represent the probability that the results we have gotten are due to error or chance, right? So in other words, 50.4%, let's say, of the variability we see in our push-up values is explained by its relationship with some other variable or some degree of error. Okay. That goes over our calculation examples. I'm going to erase all of this so it's out of my way. Cool. And then the other thing I wanted to show you guys was how to make a scatter plot, which we've done before, so if you feel like skipping through this part, that's totally fine. In your instructions, I've specified that you would be making a scatter plot between push-ups and pull-ups, where push-ups is the independent variable and pull-ups is the dependent variable. Now you'll recall when you make a scatter plot, the order in which you highlight your variables does impact how they go into your graph. So the x variable should be on the left, the y variable should be on the right. If, for example, we were creating a scatter plot between pull-ups and shuttle run, where shuttle run was the x variable and pull-ups was the y variable, then it might be a good idea to kind of insert your data such that your x variable is listed first and then your y variable follows. Okay, I'm going to undo that just so that my spreadsheet isn't all messed up. But keep that in mind based on the different relationships you're asked to graph in the quiz. So, if we are creating a scatter plot, we go to the Insert tab and then just choose the first scatter option. And what we can do from here is add our axes titles. My x variable should be push-ups. You could also put number of push-ups. That would be fine as well. My y variable is pull-ups. And I'm going to make this text bigger. In your title, you might say push-ups versus pull-ups, relationship between push-ups and pull-ups, that type of thing. In the instructions, I specified that I wanted my x-axis to be between 5 and 30. Reason being is that it minimizes the amount of white space in the graph and allows you to see the relationship a little bit clearer because it's more like zoomed in. So these are the basics. We can also add a trend line by going to trend line and linear, since all of our correlation coefficients in this class are linear relationships. If I double click on the trend line, I can change the color so that it stands out. I can also change the weight if I want it bigger. In the trend line options section, you can also add an equation of your line as well as an r-squared value. So I'm going to move these into this upper corner so we can take a look at them. When we look at our r-squared value here, again, we were looking at the relationship between push-ups and pull-ups. And this would be, if we multiplied it by 100, would be translated as 20.39%. We could cross-check that with our r-squared values we calculated in our matrix, and the relationship between push-ups and pull-ups gave us an r-squared of 20.39%. So, yay, we calculated it correctly. Okay, but that r-squared value would mean that 20% or approximately 20% of the variability we see in push-ups is explained by the variability in our pull-up variable. 100 minus that 20%, so approximately 80% of the variability we see in push-ups would be related to variance that exists with relationships with other variables. So, other information we can get from this graph is that there is a relationship with a positive direction, since the slope is a positive value. And that just means that, in general, as push-ups increase, or as the number of push-ups a person can do increases, the number of pull-ups they can do also increases. This logically could make sense because both of these exercises are based on upper body strength and endurance, right? So if you can do a lot of push-ups because you have strong pecs and triceps, that could also translate to pull-ups even though different muscle groups are used. Generally speaking, we're still looking at the upper body strength and endurance. Okay. It is important, though, to make sure that we emphasize that the number of push-ups a person can do does not cause another pull-up value to result. So being able to perform, let's say, 20 push-ups does not cause a person to perform 8 pull-ups, because we have several other values that align with 20 push-ups. Okay, we're just saying that it could be likely in a moderate positive relationship between the variables that the more push-ups you can do, the more pull-ups you can do. Okay, so that covers all of the things I wanted to do in Excel. Our next video will go over some analyses that we can run in SPSS.